And here is the next homework, which is planned for to be done by before the lab, by the early evening coming Wednesday. So basically, you take the three models you started from and characterize these materials by predicting their absorption spectrum. So three absorption spectra is the minimum. If you got a feedback or you have your own vision that electronic structure from the previous work is not ideal, if you see potential for improvement, you can improve it now, but it's not mandatory. I primarily want to see that you are fluent with doing and analyzing spectrum. Also, in one of the submitted homeworks, there was non-equal number of atoms. I think, let me tell it now. So in the polyacetylene cis-trans, it should be either C2H2, or if you have 2 unit cells, it will be for cis C4H4, or if you think you want to do bigger, you can do C8H8. But I noticed that some of you did C6, which if you look on this image, 1, 2, 3, 4, 5, 6, it is not periodic. So the atom number 1 and atom number 7 are not identical replicas of each other. So when needs to take 8, if you are not happy with 4. And also I see one work that had C6H5. Then it means that one of the, or maybe opposite, but imbalance between carbons and hydrogens means that one hydrogen is missing and there is a lone bond, which is it is a radical. It's interesting problem, but it is not what we characterize right now. So make sure that they're even. Also, in the pod car, the list of elements should match the list of elements in the postcard. So in the postcard you have alphabetically hydrogen first, silicon second. Then in the postcard it should be the same. If you swap elements in the postcard, it will bring some crazy results. If you swap the order of elements, then it will show like model where silicons are outside and hydrogens are in the center, which is very creative, but again, not what we are looking at right now. Okay, sorry for wasting your time on this, but maybe some of you wanted a feedback on the homeworks. So upon you create oscillator strength file for each of them and build spectra, I'm asking also to do additional work and look inside the oscillator strength file. So look on the 4 transitions. The lowest one, HOMO to LUMO, and then the 3 second lowest, HOMO -1 to LUMO, and a few others. In order to do so, you need to identify what is number of HOMO for certain model. Like it can be in our lab 2 days ago for titanium dioxide, HOMO was 32. Then HOMO to LUMO would be 32 to 33. But as soon as you take different model, this indices will be different. So it's not very complicated, but it needs some concentration and maybe a couple of cups of coffee. So I'm inviting you to look inside the oscillator strength file and parse and take from there 4 lines corresponding to these transitions and then analyze them intellectually. So you can rank them according to the value of oscillator strength, which is in the third column, and then report which transition has largest and smallest value of transition diagram, let us say oscillator strength. Oscillator strength. So why it is needed? It is not my frivolous wish to make your life harder. Some of you may benefit it in your projects. For example, but I'm not giving any specific project, but for example, Boston was interested in the silicon as a so silicon, bulk silicon, which can be material for photovoltaics and light emitting, and it absorbs light, but by the nature of this material, it does not emit light. And in some materials, HOMO to LUMO transition do not have oscillator strength, or oscillator strength tends to 0. So if you look only on the image of the absorption spectrum, then you not always able to see which transition contributes to certain line. So by analyzing individual contributions to absorption of light, one can learn more about the material. So this one probably is, it's not challenging. I'm absolutely confident in your strengths to do it, but it takes a little time and concentration, repeated 3 times for each model. And then the remaining are more like extra credit, but if you have energy, you can try. So look at values of Cartesian projections of transition dipole, which are columns, last 3 columns, 6, 8, 9. And there you may tell whether the transition dipole is aligned parallel to the growth of this periodic material or perpendicular. So it is an interesting observation, and if you will ever write research papers on periodic materials, it is something that community would appreciate your observation on. So like parallel or perpendicular. And you are welcome to stop at this point while doing homework. But if you are really, really dedicated, you can compute oscillator all and explore transitions from occupied to occupied and unoccupied to unoccupied, and compare them with the transitions that you looked before. So these transitions will be not seen in regular absorption, but if later on you explore emission, they may contribute. And there will be an interesting observation that such transitions are typically much more efficient. Their oscillators, like if here oscillator strength is around 1, here it will be around 100. So you may just meditate about it and report your observations. Whew. Yep. Thank you for investing your time into this homework. Send emails. I will be very happy to assist.